Hi, everyone. Thank you very much for joining us today. Welcome to this session about building on Azure Quantum. My name is Frances Tibble. I'm a software engineer in the Microsoft Quantum team. Day to day, I spend my time working on the Azure Quantum service, as well as building solutions with our customers. Today, you're going to be learning about all of that and more in this session, which is presented by my colleague, Anita Ramanan. I'll be acting as your moderator, so keep your questions coming in as the talk is going on. We'll have time to answer them during the Q&A session at the end. So with that, over to you, Anita.
Thanks, Francis. So hi, everyone. I'm Anita, and I'm a quantum software engineer at Microsoft also. I'm a physicist by training, but I've been here at Microsoft for about 5 years now in various software engineering roles. So I'm kind of sitting on both of the sides of the fence as far as quantum computing is concerned. On my day-to-day job, I work with customers and partners to build out custom quantum-inspired optimization solutions. I'll cover this technique off in a little bit more detail later, so I won't go into too much detail now. But today, really, I'm hoping to share some of my enthusiasm for quantum computing with you as I give you a sneak peek of what we've been building for you. So in this session, you'll learn more about where quantum can have real impact today, how to start writing quantum code, and how to run applications against a range of both quantum and classical hardware using Azure Quantum. No prior quantum computing knowledge is required, so let's get started. So as developers, I'm sure, like me, that you like to live as close to the bleeding edge of technology as is humanly possible, putting it through its paces to see what you can do with it or what it can do for you. Now, whether your passions happen to be in hardware or software or solutions, or perhaps a combination of all three of those, it's pretty hard to get much more cutting edge than quantum computing. So today, instead of giving you a theoretical overview of what a quantum computer is, I'd like to give you make things a bit real by actually introducing you to Azure Quantum. So Azure Quantum gives you access to a variety of real quantum hardware for you to use and test your code against, so that when quantum hardware is available for scale, you're as ready as you can be. Not only that, but through a range of quantum-inspired optimizers, you'll have access to solvers that will enable you to tackle some of the world's most complex problems today. These solvers emulate quantum processes using classical hardware in order to find better optima, reduce time to solution, or in some cases, do both of those things. The Azure Quantum Open Ecosystem gives you access to software, solutions, and hardware built both by us and by the wider quantum community. Now, this is where you come in. It's going to take a global community to achieve a truly scalable quantum system able to solve some of the world's most complex problems. We need to innovate together to make this a reality. Now, as you might have guessed, Azure Quantum is a service in Azure even, which means that security and scalability come baked in. This also means that your investment will persist even as the underlying quantum hardware grows and scales and evolves. Azure Quantum gives you the freedom to forge your own path towards scalable quantum computing, providing you with the tools that you need to start having quantum impact today using our suite of pre-built quantum-inspired solvers. All right, so now let's get into some detail about what we're actually building. For us, Azure Quantum represents nearly 2 decades of quantum research and investment. It will empower you to have real impact today with quantum-inspired solutions, build and optimize quantum code using our suite of simulators and resource estimators, and then test against a variety of real quantum hardware. So here you can see some of the key application areas that we're targeting with this new tech. Now, this is by no means an exhaustive list, but it should hopefully spark your imagination. To build all these great solutions, you're going to need a quantum toolkit. This is where the Quantum Development Kit and our high-level Q# language come in. They're both open source on GitHub, which empowers you to directly shape the evolution of this fast-moving field. Just like many classical languages that you probably use today, Q# allows you to write code once that will execute against multiple different targets, be those simulators, resource estimators, or in fact, real quantum hardware. You can write code in an environment that you're familiar with, like VS Code or Visual Studio or Jupyter Notebooks, for example, and make full use of powerful debugging and resource estimation capabilities to start designing algorithms today that tackle your hardest problems using as few quantum resources as possible. This will enable you to take advantage of full-scale quantum hardware as soon as possible. The next layer of the stack is Azure. Azure Quantum's tight integration with the wider Azure ecosystem enables you to make best use of existing industry-scale classical infrastructure right alongside your quantum solutions. And Azure also handles all of your quantum job management for you. Next, we come to the part that I'm personally the most excited about, the quantum hardware. Now, there are many different flavors of quantum hardware in development today around the globe, and this includes our own approach, which is based on something called a topological qubit. Now, Azure Quantum gives you the flexibility to write your Q# code once and run it on a diverse selection of real quantum hardware that are developed by our partners. For example, IonQ and Honeywell are building ion trap quantum computers, and QCI are building superconducting quantum computers. Of course, our topological qubits will also be made available through Azure Quantum in the future. So the really important thing to take away here is that with Azure Quantum, you'll be able to write lasting code and build algorithms that run and scale against a wide variety of hardware, be that classical, quantum, or some combination of both. So next, let's dive into how our partners OTI Lumionics, 1QBit, and JIJ are making use of our quantum-inspired solvers to achieve real impact today. OTI Lumionics are making breakthroughs in fast materials design, using QIO to successfully simulate the quantum process that causes light emission in a material that is used in OLEDs. 1QBit is currently using these same QIO solvers to drive innovation in drug discovery and material science through advanced computation. And JIJ is using Azure Quantum to optimize traffic with their customer, Toyota Tsusho. Now, I don't know about you, but to me, it feels kind of like it's been years since lockdown started. But even so, I can kind of vaguely remember in the distant past being stuck in traffic at a red traffic signal. And once the traffic light goes green and the cars eventually start moving, the next light has already gone red and you're once again stuck. Now, if you could optimize the timing of these traffic lights, not only could you lower your daily morning level of stress that's traffic induced, but you could also reduce emissions by reducing the number of idling vehicles. Sounds great. So how does JIJ tackle this optimization problem? The first thing they do is they map that frustrating waiting time to a waiting cost. And that enables them to express the problem in a format that's a special type of optimization problem known as a polynomial unconstrained binary optimization, or PUBO. Now, this is a type of problem where each variable can take one of two values, hence the binary, and the goal of the optimizer is to find some combination of variables that minimizes the overall cost. Now, in the case of a PUBO, each variable is able to interact with numerous other variables in that system, which increases the complexity. In fact, this is an NP-hard problem. Fortunately for us, we have Azure Quantum QIO solvers, which are designed specifically to tackle these PUBOs. Now, JIJ have been using those to great effect. In fact, working with their customer Toyota Tsusho, they have used Azure Quantum to achieve up to 20% reduction in waiting times over conventional optimization methods. And as I mentioned previously, less time spent in traffic means lower carbon emissions as well. So it's a win-win for all of us. Now that we've seen how our partners are using Azure Quantum today, let's take a quick look at what we're doing to get you started with Quantum as quickly as possible. We really want this to be something that feels approachable and something that's as straightforward as possible to use. And that starts with using familiar terminology and ideas, like the idea of a workspace as a collection of assets, or using resource groups and subscriptions to organize your resources. And you can create these resources in whichever way is most natural to you, via the Azure portal, the Azure CLI, or perhaps our Python SDK. Billing is pay for what you use, whatever the target is, and you can easily see what your usage is via the Azure portal, much like with any other Azure service that you might have used in the past. And finally, you can develop code using tools that you've used before, such as Jupyter Notebooks, Visual Studio, and Visual Studio Code. Now, before we jump into the demo, I'd like to take a minute to try and summarize some of the passion and the vision that went into building Q# and still goes into developing it. First and foremost, Q# is meant to make quantum solutions accessible and shareable across disciplines. Now, we at Microsoft Quantum are a diverse, multidisciplinary team, and we want to enable others to collaborate across disciplines in the same way that we do. So we spent a lot of energy to make it easy to build on knowledge and share ideas independent of background or education. As I mentioned previously, Q# is hardware agnostic. This means that you can run the same Q# code regardless of the underlying hardware architecture, just like with classical code today. The compiler deals with the rest. Q# is focused on expressing information to optimize execution. Our goal is to ensure an efficient execution of quantum components, independent of the context within which they're invoked. We want to ensure the scalability, not just of applications, but also of the development effort. And finally, Q# is a living body of work that will grow and evolve over time. While we have a vision for how quantum devices will revolutionize computing, we also believe that the quantum stack of the future will go far beyond our current imagination. And we also believe that contributions from you as members of our growing community are essential to Q#'s growth and evolution. Now for the demo. In this recorded demo, you'll get the first sneak peek at the Azure Quantum service. You will learn how to create a workspace that we use to solve quantum-inspired optimization problems, and also run problems on quantum hardware. You'll see how straightforward it is to write your code once and execute it against multiple targets. So let's take a look.
As you'll see, Azure Quantum is very similar to other Azure services you've used in the past. You'll first need to deploy an Azure Quantum resource into your Azure subscription in order to use the service. This resource is called a workspace, and you can think of it as a collection of assets associated with executing a quantum or quantum-inspired workload. After providing some basic information, I can select providers that will be part of the workspace. A provider is a third party that has a service offering. It might be quantum hardware, a simulator, or a quantum-inspired optimization. Here, you can see some of our partners: IonQ, Honeywell, and 1Qubit. We will add the three of them to this particular workspace. Finally, we simply need to review our settings and go ahead with a creation. I'm now all set to target problems against all of these different providers. Next, let's switch to VS Code to see how we can solve an optimization problem to balance the weights of cargo ships. This is a critical issue in maritime transportation. So what we've got here is a Python program that defines our problem and targets a quantum-inspired solver. Within the same program, I can optimize a problem against multiple targets, which will allow me to easily compare their solutions and performance. Once I create a function that describes the terms of the problem to represent the weight of the various containers, I can submit the optimization problem using just 2 lines of code. One is to select the type of solver, where I'll specify the workspace I previously created, and a second one will be used to submit the terms to the solver. With a single line change, you can instead run exactly the same problem using solvers from other Azure Quantum partners, such as 1Qubit. For the simplest problems, you'll get results returned within seconds, but you'll also be able to design and submit problems that may need to run for hours or even days to find an optimal solution. You can learn more about this optimization problem in our Microsoft Learn modules. Now, let's prepare for the scalable quantum computing of tomorrow and look at how we can execute some quantum code against real quantum hardware. As an example, we're going to take the Bernstein-Vazirani algorithm, which was invented in 1992. Now, this provided one of the earliest indications that quantum computing can outperform classical computing. This algorithm showed that a quantum computer could find an unknown string of any length using just 2 queries, whereas a classical computer would need to use n+1 queries, where n is the length of that string that we're looking for. So what exactly do we need to do to run this? In your Q# program, you simply prefix your entry point function with the @entryPoint attribute, and from the command line, you'll be able to specify the target that you want to run against. No need to change any source code. Using the Azure CLI, you only need to specify the resource group and quantum workspace once, and all subsequent commands will use these settings. Now that we're done building the project, we're going to use the submit command and specify the target to execute using the IonQ simulator. There are 3 important commands that you'll typically use here. Submit to run the program against the target, show to query its execution status, and output to see the results. After verifying that my program has run successfully against the IonQ simulator, I can now run the exact same code against actual quantum hardware. In this instance, we're using the IonQ Quantum Processing Unit, or QPU for short. Finally, I can visualize the output results from jobs that I previously ran. So to summarize, Azure Quantum allows you to work in an environment that you are used to and trust. The Azure portal to manage the quantum resources, the command line interface to run and manage your jobs, and Visual Studio, VS Code, or Jupyter Notebooks to write your own code. You will soon have access to a varied ecosystem of quantum solutions. When using Azure Quantum, you are not limiting yourself to a single solution provider. You can learn now to be ready for when full-scale quantum computers will be available, and also immediately start using quantum-inspired algorithms that can have real-world impact today.
Okay, so in that demo, you saw how you can use Azure Quantum to manage quantum resources, write code in an environment that you're familiar with, and test and optimize your algorithms using simulators, resource estimators, and real quantum hardware. You also saw how you can make use of quantum-inspired optimization solvers to have real impact today. So I bet you're eager to find out how you can actually get started with quantum computing. Your first call should be our brand new Microsoft Learn modules, which I know Francis has been putting a lot of work into over the last while, so definitely worth checking them out. They'll teach you how to write your first program using Q# and the QDK, and understand better what quantum-inspired optimization is. Also, they will help you to get a better sense of how your existing skills are relevant here and how they can be applied in this new domain. Now, those are free and available online now. Second, you can sign up for our Azure Quantum Developer Workshop. This will be a series of remote developer workshops dedicated to skilling up on Azure Quantum. Sign up, and you'll get the latest information and access to in-depth tutorials. Thirdly, you can sign up for early access to the Azure Quantum service. Signing up now will mean that you'll be the first to hear when it enters public preview later in the year. Now, alongside all of that great content, we also have lots of useful resources available at the link that you can see on your viewing pane now. This includes a new Q# coding contest, our extensive documentation site, where you can find details on how to install and get started with the QDK, and also how to contribute to it on GitHub. And you'll also find my personal favorite, our Quantum Katas, which are a series of coding challenges that will take you right from the basics of complex maths all the way through to implementing quantum algorithms. Now, these are designed to kind of be developer friendly. So, you know, it'll be kind of working through Jupyter notebooks, solving a little problem, running a test, seeing if you've got the answer right, getting a hint if not. It's a really, really great way to get started with all of this. Thank you so much for tuning in today. I, for one, cannot wait to see what you'll contribute to the quantum revolution in the future. We now have some time for Q&A. Sorry, Francis. Over to Francis, who has your questions.
Sorry for butting in. Thank you. Thank you so much for that. That was great. We've had a number of questions coming in, so I will start with one which I know you'll definitely be comfortable with. So, does quantum computing hardware process 0 and 1 like other computers?
So, yes and no. So inputs are still 0 and 1, right? Binary is still the kind of the basic unit of information that you'll be dealing with. But whereas a classical machine will be dealing with a bit, which is 0 or 1 at any one time, a quantum bit or a qubit can work in something called a superposition, which is usually where you hear the analogy of it 0 and 1 at the same time. In reality, it's a little bit more nuanced than that. But we can work with these superposed qubits and this kind of probability distribution to do computation in ways that we'll just never be able to do with a classical machine. And that's really one of the really big reasons why we think quantum computing will revolutionize the computing of tomorrow.
Cool. So the next question, can you already see some admin operations tasks in the quantum domain, or do you think it'll stay a developer-only field in the near future?
So operations research in particular is a really interesting field here, particularly for our quantum-inspired solvers. So there's lots of optimization algorithms that we'll be making several available and more kind of in the future when it goes into public preview. So those are definitely, those are something that we're actually tackling OR problems right now using. More generally, there's lots of quantum optimization algorithms as well that will run on quantum hardware eventually. So yeah, I think there's loads in this space that we can absolutely get our teeth into, like scheduling problems, for example, or traffic routing, or all sorts of operations research-based problems and solutions that we can find.
Great. Yeah, and I think just to tack on to the end of that, I know you've said in the presentation that it's a very diverse field. There's a lot of different people from all different backgrounds that we work with. Like, we're both developers, we work with chemists, we work with hardware engineers, so
yeah, mathematicians, physicists, the whole gamut. So
definitely a lot of places to get involved. So is there a demo or GitHub available internally in Microsoft about Azure Quantum already available?
No, not more. Well, not more than we've shown today. Our partners are currently working closely with us, like JIJ, 1QBit, and OTI. They're working with us to kind of hone and improve our services and prepare that for the public preview that'll come. So I'd sign up for that and keep an eye out for notifications internally and externally. But if you sign up, you'll be the first to hear.
Cool. So next one, are you planning to make it possible that apps written in C# could be migrated to Q#? I think this is a tough one.
It's an interesting one, right? So let me tackle the kind of more fundamental problem there. So what you're kind of asking is, should a classical code just be migrated straight to a quantum machine? And whilst yes, you technically could, a quantum computer will be able to do everything that a classical one will be able to. It's one of those just because you can doesn't mean you should kind of problems, because just like today we could use a GPU, for example, so in machine learning, sorry, let me start that again. In machine learning, you use CPU for certain tasks and a GPU to accelerate certain things when it's required. You can kind of think about quantum processors in the same way. Just because you could write code on a GPU to do everything that you would need doesn't mean that you'd want to, because it's long and it's hard and it's much more time consuming. And likewise, for a quantum computer, you want to target the things that the quantum machine will really be able to accelerate and run those on the quantum computer rather than the whole thing. So technically, yes, but you probably wouldn't want to, is the short version.
So can you give some examples of where I could contribute to the quantum development kit?
Oh yeah, for sure. So as I mentioned, all of it is available on GitHub. It's all open sourced, all of the simulator, the QDK, all the Q# stuff. So what I'd recommend is popping over to GitHub and checking out some of the open issues, for example, or getting involved in some of those discussions, or downloading the QDK yourself, trying things out, seeing if you hit any bugs, and contributing in exactly the same way as you would for any other open source project. We'd love to hear from you.
The next question we have, what is the maximum number of qubits available?
That's also a really good question. So there's a distinction to be made here, right? So we have the concept of a logical qubit, which is the ideal qubit that we want to use for computation. And then we have the concept of a physical qubit, which is like literally like the single units of quantum stuff that we're using for computation. So that could be an ion, for example, or a photon, a light particle, or a topological qubit, like any number of different quantum systems. Now, one logical qubit is made up of many physical qubits. And the reason for that is that qubits are really susceptible to noise, and they lose their nice, neat quantum states quite easily by interaction with the environment that we just can't shield from. So we need lots of extra qubits to correct for errors, right? So when we say how many qubits do we have, I think there are systems out there with up to 100 or the order of about 100 physical qubits. But the logical qubits is where the real kind of key number comes across. So as to that depends on the error rate of that particular hardware. It's harder to answer.
Yeah, and particular qubit counts for the different devices that will be available through Azure Quantum. That kind of information will be made available once it's moved into public preview.
Yeah.
Yeah. So you shared a few examples of some customer scenarios in your presentation. Are there any specific problems or industries that are best suited to quantum work today?
So for the quantum-inspired solvers, anything where you can think of a problem with probably of the order of hundreds to thousands of variables that are heavily interacting, where the optimization, like the cost function that you're trying to optimize, is quite rugged. It's got lots of false optima. Those are the problems that we're looking for. So things like logistics problems, things like scheduling, things like financial risk modeling and things. Like, we're working with a lot of different customers and we're looking at a lot of different industries. So just complex optimization problems, really.
Yep. So perfect. Thank you very much, everyone, for tuning in. Thank you for all your questions, and especially to Anita for this presentation today. I'd say a few things that you can do now. Definitely go and check out the MS Learn modules, get involved. There's a number of things that you can do, such as contributing to the quantum development kit, getting involved with the coding competition that will be coming up soon, and a number of other ways like the developer workshop. So thank you, everyone, and enjoy the rest of Build.
Thank you very much.